Well, it's morning here in New York, afternoon, I assume, for a significant portion of the population. And I think my talk today will fit rather nicely with Pukraj's talk beforehand. This is a narrow um, and fairly deep dive on a topic of synthetic inertia. You'll notice right off the bat that that's not what I'm calling it here. And I'm going to dive into that. We'll look at some of the technical issues of how we use the inertia from wind turbines to provide frequency response, and then look. I think will fit very nicely with the previous speaker. Take a deeper dive into some unintended consequences or risks associated with not getting your grid code quite right. So I want to acknowledge this. So a lot of this work was done by me and colleagues back in the days when I was at GE. Most of it has been published in various places, and some of these systemic results are from various work that was done for the National Renewable Energy Lab under DOE sponsorship. So this kind of work doesn't happen in a vacuum, and I want to acknowledge that. So a few high-level issues here that I believe will not be news to anybody that's studying renewable integration, but it sets the stage. The fundamental reality of wind turbines is that they interface with the grid through power electronics that isolate the inertia of the actual drivetrain from the grid. So this is often just given as a truth that all inverter-based resources contribute nothing to system inertia unless they are told to do so. So as inverter-based resources, wind, solar, displace conventional synchronous generation, the inertia declines, things change faster, all things being equal, you get deeper, faster frequency excursions from disturbances, and that represents a reliability risk. I kind of hope that isn't a surprise to anybody on the call. And we're going to look deeper here into the accessing that stored energy in the drivetrain of a wind turbine to help stabilize frequency. So this lecture has parts of this lecture are actually been around quite a while, and that previous slide is more than a decade old from when I was working at GE and we were rolling out the first commercial versions of synthetic inertia. And we use that language. I use the language virtual inertia. We thought that would be a great way to communicate with the industry. So we were thinking, all right, we're gonna make the turbine's inertia accessible to the grid in some fashion and deliver energy. Let's make, we're going to synthesize the inertia. Let's call it synthesis. But as we go forward here, you're going to see that it's misleading, and it has frankly caused problems as the industry has learned and is experimenting and developing new controls. And at the end of today's lecture, I'll talk a little bit about grid forming inverters, but for the most part, we are going to talk about frequency response of present technology commercially available turbines. So this is a relatively new slide, and it dives into some of the language that is becoming fairly broadly industry standard. This is slightly US centric. So for those of you that don't recognize the acronyms, NERC is the North American Electric Reliability Corporation. That is our North American reliability entity. It is a quasi-governmental institution of significant technical expertise that is staffed and supported by all of the North American power industry, the utilities, whatever utility means anymore. So these are the folks that set the reliability standards of performance. And in recent years, frequency response, for all the reasons that I put in the earlier slide, have been a concern. The quality of frequency response was observed to be declining a decade ago in North America, and they that launched some sort of soul searching. You see this asterisk here. There's a frequency response initiative report dated October 2012. I know that seems pretty old, but that report is really excellent. And if you're interested in understanding how particularly the North American grid, but more broadly system physics works in terms of maintaining frequency, that's a great document. But it introduces some language that is important for today's discussion. And we are talking about using the inertial control, using controls on the wind turbine to respond to frequency. But it isn't system inertial response. It's not SIR in the language of emerging market constructs and operational constructs around the world. What we're doing is using the inertial energy that's stored in the wind turbine in a fashion that is not unlike using the energy that's stored in a battery or some other energy producing resource to actively respond, measure frequency, and stuff megawatts into the system quickly. In the language of NERC, that is a fast frequency response. So there's another piece of language that I will introduce, maybe hopefully not introduce, because hopefully you have encountered it. But if not, you'll notice the use of the word essential reliability services, okay, ERS, on this slide. That language is replacing older language where we used to call these things ancillary services. All right, so you have, power and everything else. And the industry had decades of practice that said, okay, everything else are ancillary services, reserve services and regulating voltage and providing secondary frequency response, et cetera, et cetera, et cetera. Those are all ancillary. NERC and other members of the industry are pushing that language aside because, sort of simply stated, there's nothing ancillary about them. They are absolutely requirement. They are essential to running a reliable system. So, and NERC and others have tried to segregate the idea that there's a market. Maybe you need to pay for this. Maybe you need to mandate it. NERC doesn't care how you get it. NERC is not a market entity. We have a different regulator for that in North America or in the US called FERC. So if you don't get confused between NERC and FERC, NERC says you need to have control of your frequency, and that's what this frequency response initiative report is all about. So that's the ability to detect frequency and add it to the grid is a fast frequency response. So we have abandoned, at least we're encouraging the abandonment of talking about the controls that I'm going to spend the next half hour talking about as synthetic inertia. They are inertia-based fast frequency control. So it fits with what Pukraj was saying. You will continue to see things like synthetic inertia is required, but it's a poor moniker for what is really going on. The other thing that fits into this is so-called primary frequency response. And primary frequency response has historically been what has been delivered by governors on synchronous machines. So frequency drops, the governor sees the speed as a proxy for grid frequency decline and puts more fuel into the turbine, whether it be a fossil turbine or a hydro turbine. That's been the mechanism. That is so-called primary frequency response. It is sustainable And in that sense, it is different than fast frequency response, but these things overlap. It's partly a question of speed and sustainability. So as you're working in this frequency response space, some of the language has evolved, and some of the language is a little less precise than you might like. Exactly where does fast frequency response stop and where does primary frequency response start isn't crisply defined. So let's dive into this idea of inertia-based fast frequency response, synthetic inertia, he says parenthetically. Right? The idea here is that a wind turbine has got many, many tons of rotating mass. So most people that haven't been involved with the industry sort of look and say, what do you mean there isn't any inertia? That's obviously nonsense. The point of the grid is that that inertia is isolated by the power electronics from the grid unless you actively pursue that. And that's what this control is all about. So many, many years ago, we have sort of said, all right, what do you want? Well, more than a decade ago, the idea was, let's see if we could replace the energy that is delivered during a frequency event of a familiar synchronous machine with the power electronics. Well, synchronous machines, fossil and hydro, tend to have inertia constant somewhere in the neighborhood of 3 to 4. And obviously that changes with technology and size and all sorts of things, but that kind of ballpark. So the early grid codes and the earliest synthetic inertia grid code, before we kind of adopted this language, came from Hydro-Quebec. And I'm actually going to show you some Hydro-Quebec work that was from the original designs of synthetic inertia. And the idea was, okay, let's get as much energy into the grid as you would get out of a synchronous machine of inertia constant 3.5. It is really important for today's discussion, and I'm going to say this a few times, and it's more important than it has ever been, is that we aren't trying to mimic. It is not desirable for the outcome of the grid, grid reliability and performance, to simply mimic the behavior of a synchronous machine. I'm going to put some of the equations up. We actually know how to mimic the behavior of a synchronous machine, but we can do better. And I'll show you doing better, something we recognized right off the bat as we were designing the first generation of synthetic controls. Okay, so we got some control knobs. I'm going to go through those, but there are some constraints. And the first constraint is a big one, and that relates also to the conversation about governor response. Normally, a wind turbine is producing as much power as it possibly can. It is capturing the maximum available energy from the wind up to its rating. So if you need more power out of a wind turbine, you can't make the wind speed go up. That has some real important implications. If it's windier than rated for a wind turbine, then there actually is more power available in the wind if you're willing to overload the turbine. And keep that in mind as I show you results farther along. But if the wind is lower than rated, then the turbine is almost by definition doing the best it can, and you can't tell Mother Nature to increase the wind speed. So the only place we can get energy is to take it out of the inertia, and that is temporary. The other thing, and Pukraj mentioned this repeatedly in a broader context, is changing the power out of a turbine changes the torque. It changes the mechanical loading on everything. So you folks on the line that maybe are researchers and you do computer simulations and you look at the megawatts, whatever, remember that as you change the megawatts on a wind turbine, you're changing the mechanical loading on the drivetrain, on the tower, on the blades. You're changing the electrical and thermal stresses on the converter and the generator, and you got to respect those stresses. So you have that to remember. And then the equally important is to remember that we basically got one control map. We can change the torque on the drivetrain, but that is serving many masters in a wind turbine. Not the least of which is that torque control is managing the mechanical loads on the wind turbine. And frankly, keeping the wind turbine healthy is higher priority than keeping the grid healthy. Okay, so let's look at how this works. This is a very old drawing. I made this drawing literally 20 years ago in the first generation of modeling documents. If you're researchers, you probably have stumbled across variations on this theme. And the wind turbine models have been evolving for 20 years. But there's a couple of fundamental things here. The key point is that the going from left to right is that as the wind comes into my stylized turbine and turns it, that's the mechanical power in your turbine generator model, and it is a function of wind speed and the rotor speed. That turns the rotor, turns the electrical rotor. Most wind turbines have gearboxes. We don't really care about that today. And then that power goes out into the stator. In a Type 3, a double-fed wind turbine, the slip, the difference between the speed of the rotor and the speed of the grid is made up by manipulating the field of the rotor. In a Type 4 full converter wind turbine, the difference is farther out, and the difference between the speed of the rotor and the grid is accomplished downstream by a converter through which all the power runs. For today's discussion, we don't care. Both of those structures, which are essentially all wind turbines, all commercial wind turbines today, certainly all utility scale wind turbines today, use one of those two configurations. Both of those have the net result of isolating the inertia from the grid and giving us very fast, very agile active power control. That fits with many of the points that Puckraj brought up in the previous talk. So these are what you should have learned in undergraduate school, right? We got the inertia torque equations. So the mechanical torque is trying to speed up the wind turbine, and the electrical torque is trying to slow it down. And when those are in balance, the machine is at steady state. When there is a difference between the mechanical torque in and the electrical torque out, that is accelerating torque. The rate at which the machine accelerates is a function of its inertia. Hopefully none of that is news to you. Those equations still apply for a wind turbine, just like they do for a synchronous turbine. What's different is the control over the electrical torque. Basically, there's very little control over the electrical torque in a synchronous machine. It is all done by adjusting the mechanical torque and the interaction of the generator with the rest of the grid. So there's a fundamentally different critter here. So this is fairly obvious, right? So if we increase the generator torque above the mechanical torque, the turbine will slow down, and the extra energy that is delivered to the grid, torque times speed, power, comes out of that J omega, right? The H of the wind turbine, just as it does out of the synchronous machine. So to summarize these 2 points, it's really fundamentally different, right? Synchronous machine, we control the mechanical power generally with fuel. The electrical power is completely passive. It interacts with the grid in some fashion related to its internal angle and the grid, secondarily the magnitude of the internal voltage of the flux. which we have a little bit of control over. But so when the grid moves, when the frequency changes, or more importantly, the terminal angle changes, the power that comes out of the machine equations is inherent. It is built into the synchronous machine, and you have no control over it. People have a tendency to think that that behavior is necessarily a good thing, but it isn't always. Inertia isn't always your friend. And that's a lecture for another day. But for a wind turbine, we control the torques, the mechanical torque, by controlling the turbine pitch, so the angle of attack of the blades, and we have no control over the wind speed. So there's no equivalent to fuel flow control. There's only how much of that is captured. Then we have a completely separate, and this is really critical, and I think most of you on the call probably understand it already, that we can actively change the electric power independent of the mechanical power. Therefore, the inertial response is solely by control action, and none of it is inherent and none of it is uncontrolled. It's a really different beast. So let's just walk through what happens with inertia-based fast frequency control, with synthetic inertia. We trip the system. I'm going to go through a time simulation here, so I'm going to go back and forth between these two figures. But the frequency starts to decline. Unlike actual synchronous machine, the control needs to detect that the frequency is changing. Pukraj made a really important point, which I'm going to repeat here, and that is when you're measuring frequency, it takes a few cycles to make sure that it really is a frequency event. Remember, frequency is just the time rate of change of the angle. So, for example, if the angle takes a step over one cycle because of a switching operation, a step translates into possibly a massive off the scales frequency change. You can't figure out frequency for control actions in a cycle or two with any confidence. People forget that. Researchers forget that. Do not forget that. Real system, the waveforms are messy. Other things masquerade as frequency changes. So it takes time to respond, whereas the flux equations respond instantly. That's the difference between synchronous inertial response and controlled fast frequency response. Okay, so the fast frequency response sees the frequency change. It instructs the wind turbine to increase the power. The power is delivered to the grid in a controlled fashion, and that helps the grid. But as we suck energy out of the drivetrain, because the wind isn't delivering more power, the wind turbine slows down and it gets less lift out of the turbine blades. So in addition to delivering more megawatts than we were entitled to, we're getting less megawatts in. While this is happening, we're buying time for other stuff on the grid to respond. All right. So after a while, the synthetic inertia, the IBFFR, has to stop asking for power and let the wind turbine recover. So synthetic inertia is absolutely and necessarily a temporary measure, and it is there to buy time for other fast frequency response, or more specifically, primary frequency response from other resources to fill in. So the only thing that synthetic inertia does, the only thing that inertia-based fast frequency response does for the grid, is it buys time for other things to act. And if there isn't something else ready to act, then it does you no good. This is a nuance that it's not a nuance. It is the overriding consideration for delivery of fast frequency response from wind turbines. So I put this slide in here just to remind you about the reality of operating a wind turbine. And that is, you pick, the wind turbine's mission is to deliver 1 per unit power if it can. So I put 2 arrows on here, and this is the speed curve actually, for different wind speeds. This curve, if you've never seen it before, I won't spend a lot of time, but it tells you the reason why we need to have variable speed wind turbines, not synchronous wind turbines, because we want to be at the top of each of these colored curves, because the top of those colored curves is maximum power, which equals maximum money. And the function of a wind turbine is to make money. All right. The fact that it makes power along the way is incidental. So when we extract energy from the wind turbine, it slows down and we move from the green arrow to the red arrow, and that contributes to the backlash. We need to make up. We are borrowing that energy, not creating it. So this is one control structure. This is the original GE wind inertia control structure. And I want to emphasize again to you researchers, this stuff's been around for a while. This figure results from the work that we did, that I did with a team at GE 14 years ago. All right. These things have been commercially available for a long time. So, but they keep changing and getting better, and there's questions about the grid cut. So this basically, I'm not going to drag you through all of it, but basically measure frequency, shape the thing to try to get the right signal, and inject an incremental torque command to the wind turbine. This is work from the original design, and there's 3 things on this that I want you to take away. So these are cases where we're working on the Hydro-Quebec system, where they were worried about the loss of inertia and making the frequency excursions worse. They have lots of primary frequency control, but the hydro turbines are relatively slow. So that's a great place for this inertial control because, as I said, it's buying time. So from the blue case, which is a reference light load, low load, big event frequency excursion that's barely tolerable for their system, you see it's actually deeper than their under frequency load shedding, but this is just for illustration. We come along, we shut off some hydro machines and replace it with wind. This is relatively small. Back in the days when we thought 10, 20% wind penetration was a really big deal. So this is 1 gigawatt out of 14. Obviously today that discussion has radically changed. That's really important when I'm going to show you the next slide. So the frequency excursion gets a little bit worse. When we turn on the wind inertia, we get a huge benefit. And that's because the timing of the megawatts delivered allows a better use of the primary frequency response. So mimicking, if we had just mimicked synchronous inertial response, we would have gone from the pink curve back to the blue curve. But with a smart control, we went from the pink curve to the green curve. But this slide shows the fact that the response is different depending on where the wind turbine is running. That causes a lot of headaches to people that expect inertial response to be exactly the same no matter where the synchronous machine is operating. So this is another aspect of the non-determinate behavior of wind in system planning. Okay, so I said several of these things on this slide. We need to respect controls, and what I want to take here is actual field mesh. So these things, note the date on these. So this is from stage tests of that inertial control at different wind speeds. So these are the averages of many tests. That's really important. We're talking about roughly 10% variation in power triggered there at about 5 seconds into these traces. These things have all been cleaned up a little bit in average. So you see, we put in a frequency signature that looks kind of like this fishhook blue curve and tell the control to respond. So these are not actual grid frequency events, but these are running wind turbines that are having a frequency signal put into the air junction and told to respond. And there's a couple things you want to see out of this. So let's just look at the red trace. The red trace is the turbines running at about 70% of rated. Okay, so they're doing the best they can, and we get a increment of megawatts that is duration on the order of 8 to 10 seconds. That helps slow the decline of frequency and buys time for the primary frequency response to kick in. And then here is we need to let the turbine recover. So this is the backlash. You can't get that power without that. This is borrowed and paid back with interest. And if we extend the term of the loan, the amount that you need to pay back goes up. This is the behavior when the turbines are running at rated. So there's more wind than the turbine can handle. And these cases show the turbines being overloaded by about 25% of rated. That's pretty generous. More modern ones are a little bit more limited than that. And you notice there's no backlash. So this is bimodal. There's two very different routes of behavior. Fast forward from that work, which is quite old, to work that Damien and his grad student Lisa did a few years ago, looking at a system with a lot more wind than that previous example, and showing that if you drive the turbine too hard, you can get some undesirable behavior. So the blue trace here is work that Damien and Lisa did, showing that, yeah, we can make the frequency excursion not so violent, but the backlash causes problems. And if you push too hard, this gets better and this gets worse. Out here, the bottom of that blue trace. So you can tune this behavior to get just the right you want. So we got a great improvement, right? Red is without the control, and all these traces up here with variations on a different control. So what? Two really big takeaways, right? Unlike synchronous inertia, these controls are tunable. You can make them do what you want. There are trade-offs. There isn't just one set of settings that works good for all systems. And therefore, when somebody says, tell me how synthetic inertia works, the answer is, that's a dumb question. There's more to it than that. And there's very fertile ground for you as possible researchers in trying to figure out how to do things. So the next thing I want to talk about is, okay, so this is pretty complicated. You say, gee, all these different things on here, I want to pay for what's in the lower right-hand corner. So you're Ireland or Australia or Ontario, and you're trying to create a market for people to provide this service. You say, well, this is too complicated. Let's demand some behavior. So this was a draft requirement from Ontario several years ago, in which they wanted to specify behavior so that they could pay for it. So what you have here, the blue and the red are from Ontario, from IESO, and the orange things are notations that I added to help explain what's going on here. So the blue is for a case in which the system is running at some initial power, a frequency event occurs, it is mandated by the proposed grid code that the synthetic inertia respond by 10% of the initial power within 1 second. That's what this ramp is. And then it sustain it for 10 seconds. And then once it's released, that it can't go below 90% of the pre-disturbance power, and that the recovery time needs to be limited. So does that make sense? We're going to buy this green hash. This is the payback, and they are trying to codify how much is allowed in each of these. And I'm going to show you that the physics is such that you got to be very careful about demanding stuff that doesn't meet the actual physics. So let's go through that. So we have the amount here of the response, the duration of the response, and the depth of the relief, the recovery, right? You must have the power come back lower than the wind so that the turbine can re-accelerate to its natural frequency. And you won't find this, I think we never got around to publishing it. So I've never seen somebody else publish this. This is work I did a number of years ago, trying to point out that you got to be really careful. So if the initial power is lower than rated, which means that the turbine was doing everything it could, then each initial power will have a minimum, will have a maximum reduction on the backlash. So think about that. You can take it to the limit. If when I relax this and go to recovery, suppose I don't allow any recovery, just for the sake of discussion. Just say, give me this power and you can't recover. Well, the turbine is permanently slowed down. It hasn't had a chance to get back. Therefore, it's off the top of the power speed curve, and you're exporting more power than the wind is putting in. The turbine will stall. All right. So we clearly need some recovery power. The more aggressive we depress P recovery, the faster the turbines recover. So all the manufacturers have been through this. There was some very exciting results published from Hydro-Quebec using Enercon turbines, and that is the depth of this recovery back here, how fast and how aggressively you push the turbine back. So the more aggressively you allow the recovery backlash, the faster it recovers. So if you come along here and say, I'm not going to let you go way down, then by definition of the physics, you are stretching out the recovery. Okay. If you stretch out the recovery too much, and this is an example of that parametric space for one turbine design, this is not universal, but the shape is universal. You make the recovery longer, and the amount of energy in this orange hashed area grows. And this is the curve here at somewhere around 0.06 growing to infinity. The turbine stalls. If you allow the recovery voltage to be high, which is the right side of this, then the amount of energy that you need to recover is relatively low. So the best example here is that the orange hashed is only 50% bigger than the green hash. Back here, the orange hash is twice as big. The recovery energy is twice the arresting energy, and it goes off the chart as the turbine stalls. The blue curve is how long it takes to recover. So the more aggressively you allow the backlash, the faster you get to back to where you were. So that is the trade-off. And if you over-constrain it, and there's more detail here, which I'm not going to take the time to go through, you end up with an over-constrained system. You cannot recover, or you cannot meet the rules of the grid code. So we're pretty alarmed when we saw this thing being proposed. You can't just let the accountants say, I want this, because you don't get it. So here are some simulations that were done in support of that particular investigation. And these are, I'm sorry that these are such eye charts, but what you want to see here is there's a couple things going on. One is this is the power command for disturbance, and this is the grid frequency. All right, so there's the frequency doing one of these fishhook things for loss and a recovery. Over here we have that draft IESO spec, and after a second or so, the turbine is supposed to ramp up. We didn't actually have the ability to do the ramp, so we stepped it in this simple. All right, and look, we make the frequency better, and the system comes back very nicely. But then when we get the recovery backlash, we get whacked again. So that's a pretty ugly outcome. This recovery over here is almost as bad as the initial event, and that's quite disturbing to the system. Damien and Lisa showed conditions where this backlash is actually even worse. If we just take that GE block diagram that I showed earlier, you get a much better outcome. The depth of the frequency excursion is improved, and the frequency comes back in a relatively orderly fashion. Closed loop controls are easier to get right than bang bang open loop controls. So that's a learning exercise. And then here we tune the control to do to make it a little more aggressive. That frequency excursion is quite a bit. You can't really tell on this chart, but this is a better outcome. We got less depth and the response is stretched out. So you will see that if you start to experiment with these. We have done lots of work. So this is a public study that was that my team did for the Department of Energy, looking at widespread use and the interaction between the synthetic the fast frequency controls and primary frequency controls. At the time, we were calling this active power control. So the APC in this figure is curtailing the wind so that the turbine can get more power out on a sustained basis. So do not make the mistake of mixing up curtailing the wind turbine so that it can have sustained increase of output with this inertial-based control. Those two are independent, but this simulation shows them working very nicely together. So the first trace is a reference. The second trace is with just a governor type response, deliberately matched to have the same speed of response as the thermal generators in WEC. We could have made it faster. So you see the nadir is not that great, but the recovery and the settling frequency out here is better. If we just have the synthetic, just have the wind inertia, WI in this thing, synthetic inertia, we make the nadir much better, but the settling frequency is the same because it's not sustainable and the frequency excursion is stretched out. That is always a consequence of using these IBFFRs. The frequency excursion is stretched out. If you put them together, you get the purple, which is the best of both worlds at a cost. And this is very good response for just a few hundred megawatts in a very large system. So this is about 10% of the size of the event added to the grid. So the maximum event in this system is about 3,000 megawatts. Adding 300 megawatts of fast frequency response and primary frequency response makes a huge difference of almost 100 or about 50 millihertz in the frequency nadir. So I said this earlier, it's hard to measure frequency and angle rapidly. Asking for extremely fast response is difficult. And you get better behavior if you slow the response down just a little bit over what you might want. So the last thing I'm going to just mention for completeness, and especially since we've got researchers on the call, I made a big deal out of this, right? This is fast frequency response. Measure the frequency, change the output. But if you're researching and you're paying attention to the space, the new debate across the industry is so-called grid forming inverters. Everything I've shown you is for grid following inverters. Grid forming inverters are more closely linked or behaviorally like synchronous machines in the very fast time frame. So we are, as an industry, moving forward. That tighter coupling has got some benefits and some problems. So there's been some very good work. Siemens has done some of the best work that's public anyway over using grid forming inverters, and they have reached the same conclusion that I reached and that many have reached, which is we don't want to just mimic synchronous machines. We can do better. So this is a discussion for another day. Maybe there have been lectures on grid forming in your 3 days. So maybe I'm telling you something you already know. Okay, so this is an interesting summary, right? There is a need. That people have been wrestling with this. This is a commercial, at least the GE offering has been a commercial offering for more than a decade. Enercon has been doing this. Siemens have been doing it. Suzlon, it has shown up in some grid codes, but it's not widespread. The understanding and coordination around the use of these functions has really been slow. It isn't widely used, really. It's still a novelty after more than a decade, and a lot of the institutional focus is on making sure they've got primary frequency response. In relatively smaller systems, this stuff is really important. So you get outliers like South Australia, like Hydro-Quebec, like Hawaii, like Ireland, that have given this a lot of attention. But it's not in any sense becoming universal. And there's another, these things are already going through into their third commercial implementation, but it becomes quite an interesting question of how they work with other resources and hybrid plants. So hopefully I met my timing, Damien, and I got a little time to take a question or two if there's any.
Yes, thank you, Nick. That was very interesting. Perhaps I can start with a quick question. Is that you said a number of times that we shouldn't try to just copy synchronous machines. So I suppose throwing that question back at you is, okay, that's what we shouldn't do, but how do we work out what we should do, and how do we know that we have ended up in the right place?
Well, that's a good question. So I guess so. I'll elaborate on what the options are to not just mimic for starts, and then let me go from there. So, because this is control, even if we were to start at these relatively, I don't want to say simplistic, but the understandable condition of saying, all right, I'm gonna write the synchronous machine equations as they exist. I have the ability to make H variable. So you can ask all sorts of questions like, should H be situationally dependent operation condition? Does it need to be symmetric? Should H be a big number on the way up and a small number on the way down? I can do all sorts of stuff. So you got a bunch of knobs to play with, even if you want to stick with the synchronous machine equation. So why not? Why do I keep saying don't just mimic? We've got a century of designing power systems where we've taken inertia as a given and designed the system around it. And we've gotten, in the course of that century of practice, sort of taken the fact that it's a given, not negotiable with synchronous machines, as virtue, but it isn't. So, for example, the presence of inertia in an exporting system. So we have this a lot in North America where the wind is off at the edge of the grid. And when you disturb it, right, everybody on the call probably learned about equal area criteria and transient stability in undergraduate school. And you're constrained by dissipating the acceleration energy is accumulated during a disturbance before the system loses synchronism. Well, you're not stuck with that. So grid following, default grid following wind turbines are much more stable than a synchronous machine for that particular construct. So why would you give up that stability improvement just because you're familiar with the synchronous machine? So, there are things that synchronous machines do that cause you to limit how much power you can export, how stable the system is. So you don't want to go back to the old days. Now, that's one example of a bad outcome. Inertia is very useful in managing the rate of change of frequency and rock off. So if you can capture that, that's a good thing. So you want as an objective, let's get all the beneficial attributes of the synchronous machines in one bucket and get all the negative attributes of the synchronous machine in the other bucket and see whether we can keep the good stuff and get rid of the bad stuff. The answer is going to be there's probably many ways to skin that cat, A, and B, it's unlikely that one size will fit all, that the right answer for a medium-sized island system like Ireland is probably going to be different than the eastern interconnection of the US, which is several order magnitudes bigger both in power and distance. How do you know when you got the optimum? I don't know. And as you know, I am allergic to the word optimum anyway. So there you go.
Okay, thank you. So we have a comment in or question in from George Weiss. So I think George's microphone doesn't work, so I'll read it out for you. So could these behaviors not be substantially improved by having some battery storage available at the wind turbine?
Uh-oh. Did I just cut you off? Am I still on, Damien?
You're something's happening. You're still here. But we can see your desktop.
You see my desktop, huh? All right.
Yes.
Gadzooks, that's not the right figure either.
You unshare first and then
there we go.
Yourself.
I'm trying to unshare. I don't know what it. Forget it. You see something now that isn't embarrassing. I hope. Okay, so the short answer is yes. All right. So and there's good, there's already been good work. There's commercially available batteries. In fact, I have joined a growing chorus of people that are of the opinion that grid forming inverters for battery systems are sufficiently mature that the industry should be demanding those. So, the thing with inertia-based frequency response from wind turbines is, for all the reasons in my lecture, it's not sustainable. This is a behavior that's good for about 10 seconds on a good day. Right? So my argument that it only buys time is really pivotal to understanding it. But, on the bright side, this is essentially free. Batteries aren't free. All right. So we want to use each investment and each piece of infrastructure as well as we can, subject to its own limitations. So, not that I'm pushing back, because I completely agree with the observation, but you don't get batteries for free. You can get this control effectively for free. I mean, GE and the other manufacturers charge for the feature, but it's kind of nominal. There's no energy production penalty. There's really no capital cost. There's no O&M cost, whatever. So this is a feature that will make the system run better and increase the optionality for providing primary frequency response. So the Hydro-Quebec example really kind of drives the point home, or at least maybe whatever. Hydro-Quebec has got intrinsically lots of primary frequency response capability. It's hydro dominant. The hydro plants are slow though. So in that situation, using the turbines to buy time for a resource that's already there makes tremendous economic sense. I said one size doesn't fit all. We're seeing more and more hybrid plants. Obviously, to get this capability out of a solar plant's impossible. There's no inertia. So, and something on the order of 50% of all new utility scale solar projects in North America or in the US are hybrid plants are going forward, being proposed. So the industry's doing that, and you're going to see these capabilities built into the hybrid controllers.
Okay, so start with the free stuff and then start spending money if you need to.
Yes, words to live by.
Okay, so Mustafa,
Yeah, thank you very much. Thank you, Nick, for this excellent presentation. I really enjoyed it. I have three questions, so I would like to ask them fast. One is
Okay.
that I know that wind inertia is one of the earliest commercial methods for reference power for wind turbines. But what I realized that they haven't considered the change of wind speed during recovery stage of the rotors. If the wind suddenly drops, would there be a secondary frequency drop based on your
Yeah.
model?
Yeah. Well, yeah. Based on the you know, I'm not sure. I'm not sure what I'm showing you now. Sorry, good. But
You're showing your
Yeah.
slide. You're showing your slides. So yeah.
okay. Uh, yeah. Let me just go to this one. Right. So here, this is a minute. Right.
Mhm.
And the interesting stuff in this event is 20 to 30 seconds. Um, the short answer is yeah, who cares? Sorry, not to be glib about it, but wind speeds don't change much in 20 seconds, and certainly the aggregate behavior across a wind plant with multiple turbines, um, that aspect in this 20 seconds where basically everything is done is is lost in the lost in the noise. Because remember, you tend to, we run simulations and, and you show a wind turbine, here it is, even in this case, right? Uh, before the disturbance, it's flat, the output's flat. You realize that's nonsense, right? The
Mhm.
output of a wind
Yeah.
turbine is never flat. So there's just a lot of noise in this world. So that's my answer to that question. Yeah, it's real, but don't use that sharp a pencil to be engineering anyway.
Right, thank you. And the second question is that for Ontario, the grid code, they mentioned 10% incremental power during the inertial control to buy time for frequency regulation. But let's consider the situation when we have low wind speed, which is very close to the rotor stall. If we suddenly increase 10% incremental power, we will reach to rotor stall.
Yeah, yeah. So I guess two pieces to that answer. So I put this figure up. Note that that's 10% of P0, not 10% of rating. Okay,
Mhm.
that's important. So if the turbine is running at 40% of nameplate, it's already way down there. But the increment now is to go from 40% to 44%, not 40% to 50%. That's
Mhm.
so that makes the question you raised, which is absolutely correct, a little less scary. But yeah, at lower
Yeah.
and lower power, you basically just don't get this. And quite honestly, I show these cases, these tests here are for 1.5 megawatt wind turbines. That tells you how old this is, right? Because I don't even think GE makes turbines that small anymore. So the 600, that's 40% of nameplate. So it's still working okay. There was a set of tests down at 20%. I took those off. It's terrible.
Mhm.
The turbines just don't have anything to give,
Mhm. Right, right.
right? So that they don't stall. So yeah, having a grid code that demands a delivery way down below something, and you could debate this, but something like 30 or 40% of nameplate is stupid. It's not going to. You just can't. The physics don't work. So yeah.
Right. Yeah, thank you. And the last question, before we move to other uh, participant, in a lot of research works, they mentioned that the rotor stall limit for, let's say, DFIGs is zero point 0.7 per unit. Is there any reason behind it? I asked this question to quite a couple of experts, even from National Renewable Energy Laboratory, but I didn't get quite clear answer.
I mean, the when you have there's a couple of things going on there. One is by the time the rotor speed gets down to 0.7 of nominal, you really have a a massive collapse of you have
Right.
the torque delivery is just way off the curve now. The other thing is that, so there's just an aeromechanics question that isn't particularly a function of what the converter is. The other thing is, though, the frequency, right? The slip frequency now. So on this drawing, by the time you get to a slip frequency of 0.7, right? So it's negative 30%. The frequency at which you are exciting the rotor is now 30% of nameplate, and at under frequency, you have power going into the rotor. There's a complicated relationship between the slip and the direction of power through this. So you have to be very mindful both of the frequency, the volts per hertz, and the ampacity of the bridge. So there's nothing that says you can't build a machine that could tolerate even deeper speed excursions, but there's no good motivation to do so. And it's not completely unlimited for a Type 4 too, because you still got volts per hertz and other issues at very low frequency, even for a full converter. It's less driven by the converter and more driven by the insulation and the flux management in the full converter. So full converters probably can't go much lower than that either, although the physical limitations are a little different.
Yes. Thank you very much, Nick.
Yep.
Thank you. I'm going to give the last question here to Chao Wu.
Hello, Nick. Thank you for your last presentations. And I'm Chao from Aalborg University. And I'm ask a very quick question: is that do you think that we can use the Type 3 wind turbine systems for a better inertial support than the Type 4 system? Because the Type 4 is use a converter to connect to the grid. So the overcurrent of the converter is very limited. But for the Type 3 generator, with the DFIG is directly connected to the grid. So it can use the overcurrent of the generator, so you can support more power during the transient process. Is that?
You're into maybe that's there's so many design considerations that dictate overload. It's not just current, it's internal voltages, it's insulation stress. There's end winding stresses. There's a whole bunch of stuff, and I'm not a machine designer. It is a fact that we see in some classes of behavior the fact that the stator of the double fed machine is directly connected to the grid is beneficial. I think that this aspect, it's going to be design specific. So I'd be quite reluctant to make that generalization. It's possible, but not a given.
Okay. Thank you. And maybe one more is about your operation is always under the MPBT point, yes. So for if we want to do the inertial support where we just run it in a deloading operation, like to over this speed, and then if you want to decrease your speed, you can enlarge your power, so it can buy more time for the power support.
Yeah, I think that's an interesting point, and I guess I don't know how much that's been explored. It is what you just described a little bit is a variation on curtailment, right? You can't have it above the MPBT without a production penalty, right?
Yeah, it's like that. Yeah, but we'll lose some energy. Yeah.
so you're making a trade-off there that it's an interesting question. But it's not